this is the question. First, I will explain the question. Here we need to find out the RMS current through the diode, right? So to find this RMS current, first we need to find out the equivalent resistance between this point. Let us say this is the point A, this is the point B. We need to find out the equivalent resistance between point A and B, right? So how to find out the equivalent resistance between point A and B? How to find out the equivalent resistance between these points A and B? So let us say this is the point A and this is the point B. To find the equivalent resistance between the points A and B, first we need to find out the symmetrical nodes. How to find out the symmetrical nodes? This is a three-dimensional circuit. It is not a two-dimensional circuit. Okay. So I will take from A to B R1, R2, R3. This is one path. Okay. In this path, I'm encountered R1, R2, and R3. Okay. I will take one more path here. This is R1, this is R2, this is R3. This path also I'm encountered R1, R2, R3 only. Okay. First I'm encountered R1 and then R2 and then R3. In this path also, first I'm encountered R1 and then R2 and then R3. Right. I will take one more path here. This is the path. First R1, then R2 and then R3. Right. Same. Then I will take one more path. First R1, then R2, then R3. So what are the symmetrical nodes here? See, if it is a two-dimensional plane, I will write two-dimensional plane. R1, let's say R2 and R3. Let us say like this. This A, this B. This is a two-dimensional plane. Okay. So first I will represent the symmetrical nodes here. Then we'll understand clearly. See, this is the path here. This is A, this is B. The first path, same, I will take R1, R2 and R3. This is the first path I'm taking, A to B. This is the second path, right? I'm taking A to B. So what I have encountered in the first path, this is R1, R2 and R3. The same sequence I have encountered R1, R2 and R3. So if we calculate voltages at this point, after R1 I have one node, after R2 I have one more node, after R3 I have one more node. Here also in this path, after R1 I have one node, after R2 I have one node, after R3, okay, this is same node only. If we calculate here, let us say this is V1, let us say V2, let us say this is VA, this is VB, right? If you calculate V1 and VA, you will get same voltages. If you calculate V2 and VB, you will get same voltages. V2 equal to VB. In the same, this is this two-dimensional structure. So, but here we have three-dimensional structure. Here we need to find out the symmetrical voltages here. So for that, first path here, this is the path. First path I have taken. This is the first path, A to B. After R1, I will assume this is a V1. After R2, I will assume this is the V2. Okay. After R3, let us say this is B, so VB. Here A, we have VA. Okay. Next, in the second path, this is the second path. This is the second path. After R1, I will assume V1. After R2, I will assume V2. After R3, this is the VB. Let us say VB here. And the next path also. The next path. This is the path. Third path. Middle line. So after R1, this is V1. After R2, this is V2. Right? Both are same. After R3, this is VB. Both are same. Right? VB only. One more path. After R1, anyway, assumed already V1. After R2, this is V2. This is already assumed V2. After R3, VB. Okay. So these are the symmetrical nodes. At these symmetrical nodes, we will get same voltages. Let us distribute the current. So first represent the voltages where the voltages are equal. This is VA here. This is VB. After R1 we have V1. And everywhere after R1 we have V1. Those are same. VA, V1. After R1 we have V1. Okay. Next. After R2 we have V2 in everywhere. After R2 we have V2. Here also we have V2. Here also after R2 we have V2. Next. After R3 VB. This is after R3 VB. This is also after R3 VB. Right. Now distribute the current. Here let us say I. The current is I flowing here. Here we have three paths. Here is one path, here is one path, here is one path. But what is the current in these three paths? Okay, suppose in this path below line, the current is VA minus V1 by R1. In middle line also, here VA minus V1 by R1. Here also upper one, VA minus V1 by R1. Okay, the currents are same. These three branches. So this current will divide equally. Here I by 3, here also I by 3, here also I by 3, right? Next, after V1, we have here, this is R2, right? After V1, after R2, we have V2 voltage. Same, here also. After V1, this is R2, this is V2. There are two branches. Here the current is I by 3, right? And the current should be divided here, here and here. Two paths are there. But how the current divides equally? Why? Because here the voltage is V1, here the voltage is V2. The current is V1 minus V2 by R2. Here the voltage is V1, here the voltage is V2. The current in this branch also V1 minus V2 by R2. The current divides equally. Here I by 3 is there, total current. Here I by 6. Here I by 6. Right? Next, I'll come to below line. This is I by 3. Right? Here V1. After V1 we have R2 and V2. After V1 here also we have R2 and V2. Here also current divides equally V1 minus V2 by R2, V1 minus V2 by R2. This is I by 6. This also I by 6. Right? Come to lower line. This is I by 3. Here, this is I by 3. Here V1 is there. Here V2. And here also V2. So current equally divides. This also I by 6. This also I by 6. Okay. Now, so here I by 6. Here I by 6. If these two adds here I by 3. Next here I by 3 current, and here also here I by 3 current is flowing. Now here I by 6 flowing, right? Here also I by 6 flowing. These two adds here, you'll get I by 3. Now here I by 6 flowing, here also I by 6 flowing. These two adds, you'll get I by 3 here. At this point here I by 3, I by 3, I by 3 adds, you will get I, right? Same current came, same current, right? This is how we have to distribute. So now we'll again distribute this. Here the current is I, this is I by 3, this also I by 3, this also I by 3. Here I by 6, this is I by 6. Now here also I by 6, here also I by 6. These two I by 6 adds, you will get I by 3 here. So here I by 3. Now here I by 3 is here. This is I by 6. This is I by 6. This is I by 6. Here I by 3. This is I by 6. This is I by 3. This is I. Okay. This is how we have to distribute the current. Now write in the KVL here. Okay. Equivalent resistance we need to find out between A and B. Okay. So VAB equal to VAB. Take any path. KVL. Write the KVL. I am taking the outermost path. This is the path I am taking. VAB. VAB equal to I by 3 into R1. Next I by 6 into R2. Next I by 3 into R3. That's it. Now VAB by I. This is the equivalent resistance. This R1 by 3 plus R2 by 6 plus R3 by 3. This is the equivalent resistance, right? I will take one more slide. What is the equivalent resistance we got? VAB by I. That is R equivalent. It is R1 by 3 plus R2 by 6 plus R3 by. This is the equivalent resistance between A and B. I will draw this. This is R equivalent. A and B. And we have a diode and a voltage source. This is 10 sin t. This is I of t. We need to find out RMS current. Okay. This behaves like a half wave rectifier. If you know the formula, directly write IRMS for half wave rectifier is Im by 2, where Im is Vm by R equivalent. What is Vm? 10. R equivalent, we got R equivalent. That's it. If you want, I will tell you IRMS value how to find out. IRMS square equal to integral 0 to t I square of t dt 1 by t. This is how you have to find out IRMS. To find IRMS, first I need to find out I of t, because it is a sinusoidal voltage source and we have a diode in the circuit. So this diode is on when this V of t, this is Vt, when it is positive, and it is off when it is negative. For negative half cycle current is 0. For positive half cycles current flows. That current is 10 sin t by R equivalent. It is for positive V of t. We have It is 10 sin t by R equivalent. R equivalent is this one. This is the R equivalent we got. For negative V of t, It is 0. And It is a periodic signal, sin t by R equivalent. It has the time period. It's a 10 sin omega t. T is 2 pi by omega. Omega is 1. T is 2 pi. So substitute all these things in this equation, you will get IRMS is Im by 2. This Im by 2, where Im is Vm by R equivalent. Okay, that's it.